Hey everyone, this is Mr. Davidson. This is going to be our fifth lesson of the Trigonometric Identities and Equations unit. So trigonometric identities are, identities is an equation that is true for all values or all angles. Any angle that's put into an equation will work for a trigonometric identity. You would have done some proving of trigonometric identities last year. This year we're going to do more of that and a little more complicated proofs, but for now we're going to start off just kind of refreshing the idea of proving identities and how we prove an identity. We'll start off looking at just some refresher identities that you would have talked about last year. So tan of theta, that is always equal to sine of theta over cosine of theta. That's a trig identity. That is something that is true for every single angle. This equation is always true. And this is one of the most basic identities that you would have talked about last year. Conversely, cotangent of theta, so the inverse of tan, that is cos over sine. So that's another identity you would have talked about last year. If we square an identity, so tan of theta, if I were to square this, the way we write a squared trig function is the square gets put in the middle. So tan squared theta, that's tan theta times tan theta. So it's sine theta cos theta times sine theta over cos theta. Sine theta times sine theta, that's going to be sine squared theta. Cos theta times cos theta is going to be cosine squared theta. So tan squared theta is going to equal sine squared theta over cosine squared theta. And similarly, cotangent squared theta is going to be cosine squared theta over sine squared theta. These are going to be useful for some of our proofs, so I just want to make sure we're all comfortable with those identities. When we're proving identities, we want to use proper proof format. Your teachers last year may have told you pick one side and stick to it. In general, that is what we want to do. I tend to be much more lenient with that. There's sometimes where you'll want to adjust both sides because you get stuck on one side of an equation. It is okay to manipulate both sides, but you just want to be careful that what you're doing, you're using the trig rules and only changing things accordingly. For the most part, we will only use one side, but it's okay to manipulate both sides in order to help you. We will use our algebraic skills, working with fractions a lot, finding common denominators, distributive property, factoring, all that fun, but we'll also use special identities that we learn over the course of this unit that will help us. And that's why we're proving all these identities as we go along, is now we can use them going forward. So we'll look at our first example here. And this will just all be basically examples today. Cos x tan x over sine x equals 1. In general, always start with the more complicated side. More complicated doesn't necessarily mean bigger, but more terms. It's easier to simplify then make something more complicated. Also, generally, we want to get first everything into a sine, cos, and tan. Again, not always, but almost, I'd say 80 to 90% of the time, get everything to sine, cos, and tan. Once you get it to sine, cos, and tan, get everything to sine and cos. It's a lot easier to work with a limited amount of trig terms instead of all 6. So here, we're going to turn tan, we're going to focus on the left side. And so cos of x, tan x over sine x, that will become cos x, tan is sine over cos, over sine. So here we're multiplying cos by something that's being divided by cos. So those coses cancel out. And that just leaves us with sine x over sine x. And then, of course, sine x divided by sine x just equals 1. So then, well, this is equal to our right side. Our right side was just 1. So left side equals right side. And I'm not sure if this is something we would have talked about last year. Generally, when we're doing proofs, we write, therefore, QED. The QED is it's a Latin abbreviation. Basically, it's telling us that this is satisfied. This equation, this is an identity. But more or less, just saying left side equals right side, we just want to prove whether or not this is an identity. That's all we're looking for with these questions. We want to make sure that the left side always equals the right side. Number 2, cos squared x equals sine squared x over tan squared x. So again, we're going to start off with our more complicated side. That is our right side. So our right side, sine squared x over tan squared x. We're going to, again, change everything into sine and cosines. Sine and cosines are easier to use than using sine, cos, and tan. So tan becomes sine squared x over tan, or cosine squared x. If we're dividing by a fraction, it's the same as multiplying by the inverse. Sine x divided by sine x cancels out, and this just equals cosine squared x. So our left side equals our right side. Therefore, QED. Let me just double check exactly what that stands for. So I give you, I'm not just saying it. So it means, I'm not going to try to pronounce this. I don't know how to pronounce Latin. But it's an abbreviation. It stands for this, the Q, the E, the D. And in English, this basically means that which was to be demonstrated. So basically, it's what we were trying to show, we proved it. The left side equals the right side. We proved what we set out to prove. Let's go back to our identities. A couple more from last year that would have been popping up over and over that we've talked about a little bit this year. your reciprocal identities. So sine is the inverse of cosecant, or vice versa. Cosecant is the inverse of sine. Cos is 1 over secant, or secant is 1 over cos. Tan is 1 over cotangent, or cotangent is 1 over tan of x. So these 6 identities, those are our reciprocal identities. Those also come in handy. And as I mentioned before, generally if we see a secant, we see a cosecant, we see a cotangent, it's easier to work with sines, cosines, and tans if possible. Sometimes we need secant, cosecant, cotangent, but most of the time we can steer away from them. So we'll look at our first example for this section, which is sine of x, cos of x, tan of x equals, or sorry, cotangent of x equals tan of x, cosecant x in the denominator, cos of x in the numerator. So some of these, they both look about the same amount of complicated. They're in the completed lesson, they show you multiple ways to do it depending on which side you look at. I'll show you one side and I'm sure you can figure out the second. So let's look at our left side is sine x, cos x, cotangent x. We have a cosine. We don't need to change our cosine. We kind of want to look for clues. Really, all solving identities is like a puzzle. Sine of x is 1 over cosecant of x. Cosecant x is in the denominator. So that leads us to see we should go from a sine x to a cosecant x. We already have cos of x, don't need to change that. And then cotangent of x, we need to end up with a tan of x. Well, perfect, cotangent is 1 over tan. That works out. And if we multiply this all together, cos is really cos over 1. So 1 times cos times 1, we get cos of x. And in the numerator, we get cosecant x cotangent x. Oh, that's our right side. Perfect. Left side equals right side. Therefore, QED. Therefore, we proved what we set out to prove. Number 2. Cosecant theta times 1 plus sine theta equals 1 plus cosecant theta. Again, on the completed note, there's 2 different proofs to this. There's one starting with the left side, one starting with the right side. If I were looking at this, it's generally easier. We have 2 different terms plus a multiplication here. This to me is the more complicated one. So if I were personally trying to solve this, I would start with the left side. Again, you can start either way. You need to find what works for you. But cosecant theta times 1 plus sine theta. We're going to use the distributive property. We know we have no brackets here, so we're going to multiply out. Cosecant theta times 1 is cosecant theta plus cosecant theta times sine theta. So here we have cosecant theta plus something. We had cosecant theta plus something. So let's focus on our cosecant theta sine theta term. Well, cosecant theta, that's 1 over sine theta. Times sine theta. Those sine thetas will cancel out, and we'll get cosecant theta plus 1, which is the same as that 1 plus cosecant theta, just rearranged. That is our right side. Left side equals right side. Therefore, that identity is always true. Another identity you would have talked about a lot last year is the Pythagorean identities, which is sine squared theta plus cos squared theta. That always equals 1. And there's 2 more that come from just rearranging this. Sine squared theta is 1 minus cos squared theta, or we could isolate cos squared theta and we get 1 minus sine squared theta. These 3 are known as Pythagorean identities. There are more Pythagorean identities that we'll look at as we move along, but for now, that's the main one that we'll focus on, and that's going to become useful in this next example. Sine of x, cos of x, tan of x equals 1 minus cos squared x. Here we have 2 terms. Here we have 3 things being multiplied together. We only really have 1 trig function to work with here. Here there's a little more to work with, so we're going to start with the left side. And again, generally, especially if we don't see anything other than sines and coses in the side we're working towards getting, always move things towards sine and cos, or almost always. It generally just makes your life easier. So tan, we're going to change that to be sine over cos. And if we do that, we get our coses to cancel out, and then we just get left with sine times sine. So sine squared x. Well, we just saw that Pythagorean identity on the last page that you would have learned last year. Sine squared x, that can be rewritten as 1 minus cos squared x, and that's our right side. So our left side equals our right side, so we're done. Got one more example here. Cosecant squared x minus 1 equals cosecant squared x cos squared x. They both don't look great. Here we do have two separate terms. So I would generally start with that one. although that method is a little more unclear. But I will go through that one because it is a little bit more complicated. The left side to right side, feel free to check the completed lesson. That one's a little more straightforward. So we'll start with our left side as cosecant squared x minus 1. Again, I like to, actually, now that I'm looking at the completed lesson, there is 3 different ways shown. So feel free to look over. There's 2 going from the right side to the left side. Or, no, sorry, 2 going from the left side to the right side is just mislabeled. And 1 going from the right side to the left. I'm going to show you the way that I generally think about things, because that's the way I'll be going through all of these lessons, is trying to give you these strict rules to work through. So I generally will go for the side with more terms, and I like to work away from cosecants and secants and cotangents. So we're going to turn this cosecant into a sine with our reciprocal formula. So 1 over sine squared x minus 1. We have 2 terms here. We need to get it to be 1 term. So once we have fractions, in order to combine fractions into 1 term, we need a common denominator. So 1 over sine squared x minus sine squared x over sine squared x is what the 1 will become. And that gives us 1 minus sine squared x over sine squared x. You might look at this and see, how do I get from here to here? It can help to look over your trig toolbox once it's filled in. Our 1 minus sine squared x, that's one of the Pythagorean identities that we had looked at on the previous page. So that is equal to cosine squared x over sine squared x. That's a Pythagorean theorem, or Pythagorean identity. And then sine squared x, we need a cosecant squared x. So we're going to turn that back into a cosecant. If we're dividing by a fraction, we can multiply by the inverse, and we get the right side. So left side equals the right side. We are all good. Again, there's a lot of these will have many different ways you can go about them. I'm going to keep talking about what I find works for me and what I try to do to keep things simple. Look for the part with more terms. Work towards sine, cos, and tan, and then sine and cos if possible. And even in this particular one where we have to go back to a cosecant, we can still work with just sines and cosines and then put it back into a form with cosecants at the end. I just find it makes things a little simpler. There's less to focus on, and it's a little more familiar to you since you've used sine, cos, and tan much more. But that's the end of this lesson, so I'm going to end off here. Let me know if you have any questions ever, as always, but enjoy the rest of your day, and goodbye.